This subject is nothing but the analysis of these four alphabets. So we may have these four lines in another direction and B. Both of them are cross product becomes 0. Since we have to move 5 steps when similarly direction coordinate system have vectors are the quantities those who have magnitude as well as direction. Magnitude is the length of that vector if we are talking about the position vector. Vectors can be represented by alphabet. For example, we can use alphabet A to represent any given vector. But this vector A is not complete. We have to put a roof or a bar on the head of vector A. Hello everyone, welcome to today's session. Myself Dr. Sohail Rana, and today we are going to discuss about vector analysis. In earlier sessions we have seen various applications of electromagnetic field. Among that, the most understanding application is mobile phone. From mobile phone we get electromagnetic field in the space. So that part of space we will study in the coordinate system. But these parameters of electric and magnetic field are vectors in nature. When we say electromagnetic, it is combination of two words. One is electric field and another one is magnetic field. So we have total 4 parameters related to electric and magnetic field. The first one is electric field intensity, denoted by capital E. Next one is magnetic field intensity, denoted by capital H. Third one is electric flux density, denoted by D, and fourth one is magnetic flux density, denoted by capital B. As we are saying all of them are vectors, they must have direction as well as magnitude, and we represent these vectors by showing a bar on the head of that alphabet. And trust me, these 4 fantastic alphabets are very much essential throughout syllabus. This subject is nothing but the analysis of these 4 alphabets. Even Maxwell's equations are given for these 4 alphabets. So all of us must remember the significance of these fantastic 4. So let us begin with vector analysis. In physics, there are 2 types of quantities. One is scalar and another one is vector. We are concerned about the vectors, the signals which may be coming from an antenna, which have the direction as well as magnitude component. A scalar is defined as a quantity which have only magnitude, but it does not have the direction. But vectors have magnitude as well as the direction. We are concerned about these vectors. So if we consider an electromagnetic wave, it have 2 components. One is electric, another one is magnetic field. When we consider electromagnetic wave, we have to remember that they are fields. That means there are electric and magnetic force lines working in a particular direction. Second thing, they are vectors. This is our topic of today's discussion. And third one, we have to remember that they operate in space, that is a 3D atmosphere, which will come in our next sessions where we will study about the coordinate systems. If we consider one simple example of magnetic flux density, it is denoted by D. These are field lines, these are invisible lines present in space. So if we consider a wave which have 4 parameters related to electric and magnetic field. So what are these fields exactly? These fields are the lines of forces working in one particular direction. If we consider capital D, so we have 2 intensities and 2 densities. The intensities are E and H. One is electric field intensity, another one is magnetic field intensity, and we have 2 densities. One is electric flux density and another one is magnetic flux densities. Now these 2 intensities and densities are vectors. That means we have to represent them by using a bar on their head. What are these fields? These fields are nothing but the force lines working from one place to another place. A field is defined as a place where number of forces are working together. Here we have these four vectors working together in one particular direction. So, wave will have two components, one related to electric field and another one will be related to magnetic field. These waves travel in space. So, we may have these force line in space, one for say electric field intensity and another one for magnetic field intensity, and they travel in space. So, there will be one direction of propagation. So, here we have example of electric flux density lines which are crossing a surface, and we have to study them in space. Now, if we take the definition of vector, it is given by magnitude into direction. So, if we have a line as vector component d, then its differential component will be given by dl bar equal to modulus of dl into the direction of dl. So, these directions are denoted by AR cap. So, direction, we may have three different directions in three different axes. So, when we talk about space, we have to consider three axes. Here we have three axes, x, y and z are our three directions. Then its direction components will be ax, ay and az. These are also called as I, j and k. Now, let us move into the animation and check out how it works. So, vector is equal to product of magnitude and direction. AR cap is showing direction here. Mod of dl bar is showing magnitude. So, all the vectors will be given in the form of magnitude into direction. In space, how many possible directions are there? Spatial vectors or the vectors in space uses any three coordinates. If we talk about Cartesian coordinate system, there will be three axes. So, we can find out place of any given point or vector by taking their distances in three directions. Say we will have I, j and k. So, my vector may be moving in two directions or three directions. So, these I, j and k are termed on x, y and z axis. So, vertical axis will be z. A vector coming towards you we will consider as x and the remaining one as. These vectors are working in space. A space is place where we consider three dimensions. By using three dimensions, we can express any place in space. There are three axes. One axis is considered as say x-axis. Next one will be z-axis and the third one will be y-axis. The vertical axis we will consider as. So, along with magnitude we get direction in these three directions. Direction component is given by ax, ay and az. It is also written as ax bar, ay bar or az bar. In few textbook it will be written as ax cap, ay cap or az cap, but ultimately these are the directions. So, how can we find out unit direction? If vector is nothing but product of direction into magnitude, then we can say that direction is equal to vector upon magnitude. So, it can be given as AR cap equal to vector divided by mod of vector. Magnitude is nothing but the length of the vector line, and unit vector is used to give the direction of a vector. So, if we consider a 3D system, then we have to consider three directions. For example, we have x, y and z as three components, then their directions will be given as ax cap, ay cap and az cap. So, here we can see we have two directions here. So, we are considering two-dimensional system where One is AX cap, another one is AY cap. There are few dot product rules of direction components. We have to remember them. If we take dot product of similar direction components, it will become 1. So if I take AX cap dot AX cap, I will get 1. If I take AY cap dot AY cap, it will also become 1. But if we take dot product of different unit vectors, then it will become 0. If we consider third direction, that is say AZ cap, then we have to imagine this system for three directions. So AZ cap dot AZ cap will become 1. If AZ cap will be multiplied by any another direction, it will give result as 0. There are two concepts of multiplication in vectors. One is dot product, another one is cross product. Today we will focus on the dot products. Say we have to find out position of point P in space. If it is a two-dimensional space, it will have two components, one in x direction, another one in y direction. So if these two vectors are given in two directions, then the resultant vector will be addition of these two vectors. So let us see them in detail. If we have to find out a point P in 3D space, then the length of point P will depend on x, y and z component. So about AX cap, AY cap and AZ cap, we have to remember that these are nothing but only directions. If force is our vector, then it's all about how these forces are applying their effects on given points in space. Let's imagine that two vectors are coming from two different directions and striking on a point available in space. Both of them will have a particular angle on which they strike on the given point P. That means they are applying some force on point P. According to their angle, the resultant force will give moment to the given point P. It will have some effect on given point P. So we can define any plane or volume in 3D space. Here we can see there is a plane shown on a floor where it has some lengths given on x and y direction. If it is a simple plane, two axes are enough to represent it in mathematical form. So on y-axis it is moving to 1, on x-axis it is moving to 2. So x is equal to 2 and y is equal to 1 in this case. Now let us discuss addition of vectors. Vectors may be moving in particular direction. So we can refer this sign as representation of direction. Say top one is going to north, its opposite bottom is going to south, right side is east, left side is west. So if we consider two vectors, in this case we are considering force as a vector. If we talk about the electromagnetic wave have two components. One is electric field component and another one is magnetic field component. When we say that we have less mobile signal, then we have less components of electric and magnetic field intensity. When we say that coverage is good or mobile network is good, that means strength of electric and magnetic field is more. And definition of electric field intensity is nothing but force per charge available in that particular space. So force is a vector quantity. Force is important quantity to calculate the strength of electric and magnetic field in space. So for example, if we have two forces working in same direction, if they are moving in same direction, in this case both of them are moving in east direction, then they will be directly added. and the magnitude will increase. In another case, if two vectors are moving in opposite direction, one is of positive 120 newtons, another one is coming in opposite direction, its magnitude is minus 80 newton. In that case, they will get subtracted and the resultant will go in the direction of the largest force. So the final direction of the resultant force will be less. It will be 120 minus 80, 40 newton, and the direction will be towards east. Similarly, if two vectors are moving in opposite direction to each other and one is positive, another one is negative, then the resultant will be 120 minus 200, that is minus 80 newtons. The higher force is going towards west, so resultant vector will also move towards west direction. Now if a force is coming down towards south and another force is going towards north, both of them are coming in each other's direction, then in this case both of them will have a resultant direction toward the largest one, that is going towards the north. Now let us see examples where we can find out the magnitude of a vector. Here we will consider that there are two vectors. One vector is going towards east, another vector is going towards north. Now let us take one example. Here we have to find out magnitude of a vector A. It is given by 3i plus 4j. That means this vector A is going in two directions, I and j. I is nothing but x direction and j is nothing but y direction. That means it is moving in x and y direction. So A is moving in x direction 3 places, say this is 3, and moving in y direction with 4 places, say this is 4. So this is 3 and say this is 4, and the resultant will be the hypotenuse. So how we will find out the magnitude? We will find out the magnitude of vector A, where mod of A is the magnitude. It is given by square root of ax square plus ay square, where ax is 3 and ay is 4. So to find out it, we will get square root of 3 square plus 4 square. It will give us root of 9 plus 16. It will be root 25 and a value of a will be 5. So if my x component is 3, y component is 4, then the resultant will be 5. Same we can get with the use of Pythagorean rule. Like this we can find out the magnitude by taking square root of all involved directions. Now we may have vectors moving in different directions. So according to that we can use the addition and subtractions of the vectors. In similar way you can find out the subtraction of two vectors. Now let us check out dot products. We will see two methods for finding out dot products. In this example we have to find out dot product of two vectors, and the two vectors are given as a is equal to 3i plus 4j and b is equal to 5i plus 2j. So this component will be ax, this one will be ay, this one will be bx, and this one will be B y. So A can be written in the form of I ax plus j ay cap. So magnitude into direction. Similarly, B can be written in the form of I plus j. So dot product of these two will be taken with the direction components, where I square will become 1. So ax cap into bx cap plus ay cap into by cap. Ax is 3, bx is 5, so it will be product of 3 and 5. Ay is 4 and by is 2. So if we solve it, we will get dot product as 7. This is one method of finding out dot product. Then another method. These dot products can be given along with a angle. Suppose one vector is moving and it is having magnitude of 8, and another vector have magnitude of 15. So this is the resultant. Resultant is given at hypotenuse. Along with that, angle is given. Angle is 30 degrees. So to find out the vector, we have to use the formula A dot B is equal to mod of A dot mod of B to cos theta. This is the formula alternatively used to calculate the dot product. So here mod of A is 8 and mod of B is 15. The angle between two is given as 30 degrees. So A dot B will be 15 into 8 cos of 30. So if we solve it, we will get 15 into 8, 120. Cos of 30 is square root of 3 by 2. If we further solve it, we will get 60 into square root of 30. Square root of 3. So if we further solve it, we will get a value around 104. So like this also we can find out the dot product. If two vectors are perpendicular to each other, that means if their angle is 80 degrees, if their angle is 90 degrees, then what we will do? We will consider cos theta as 90, and cos 90 is nothing but 0. So in this case, the dot product of perpendicular vectors will become 0. Similarly, if we take dot product of an angle which is larger than 90 degree, then we will get answer in negative. Now, if we multiply a vector with scalar quantity, so say my vector A is multiplied with another scalar quantity, then the magnitude of this vector will increase and the direction will be same as of earlier vector. If vector A is multiplied by negative scalar, then magnitude will increase but the direction of a vector will change. So if earlier vector was moving towards right side, then after multiplication with negative scalar, it will move towards left side. Similarly, we can find out cross product. There are vectors rotating in different fields. Field is nothing but a surrounding region where the forces may be acting upon each other. We can take cross product of two vectors. Say vector A bar and B bar are our two example vectors. Here we can see vector A and B, both of them are overlapping on each other. That means angle theta is 0 between them. So we cannot find any vector component here. As vector B and vector A change its position, we get the cross product vector of these two vectors. As A progresses, we get the cross product of A and B perpendicular to A and B. As its value increases, the value of the vector A cross B also increases. It becomes maximum when B and A are perpendicular to each other. As it enters into second quadrant, the A cross B value again start decreasing. And again at the next angle, when A and B at next position, when A and B get theta equal to 0, A cross B also becomes 0. Same thing repeats in third quadrant, where A cross B goes into negative axis. Then in the fourth quadrant, again it comes towards the 0. So here we can see that when angle theta is 0 between A and B, cross product becomes 0, and the cross product is maximum when the A and B are perpendicular to each other. Now let me continue this. Now let us see these vectors cross product using this 3D animation. Here we have two vectors, vector A bar and vector B bar. Both of them are changing their position in space. According to them, the direction of cross product is also changing. You can observe from this graph, when A bar and B bar are perpendicular to each other, the cross product is maximum like this line. When these two vectors having 0 degrees difference between them, at that moment cross product is 0. These 2 points we have to remember. Now let us discuss about cross product of different and similar directions. The formula for cross product is very simple. If we consider A bar and B bar as two vectors, their cross product is given by AB sin theta into some direction, where theta is the angle between A bar and B bar. If we keep theta equal to 0, and if we consider the cross product of similar direction, for example, here if we take cross product of AX cap into AX cap, it becomes 0. It is important to note that in dot product, we have seen that dot product of similar directions becomes 1. Here we have to remember that cross product of similar directions becomes 0. When we talk about coordinate system, we may have three directions, say x, y and z, if we consider Cartesian coordinate system. Whenever we have positive direction, there will be one negative direction also. In these coordinate systems, our vectors are moving or staying in static condition as per the given example. Here we are taking two vectors, one is A bar, another one is B bar. And angle theta is the angle between these two vectors. This is the coordinate system where we are showing first quadrant, but there may be different quadrants and different negative directions. Like we have positive z axis going in positive vertical direction, there will also be a minus az cap direction which is going in negative z direction. Similarly, there will be positive x, positive, negative x, positive y and negative y directions. Let us take one example for solving cross product. Here is a question to calculate the cross product between A bar and B bar. The values of A bar and B bar is given. Same setup we can consider. We have to use matrix form to solve this example, where A bar cross B bar is given by three directions x, y, z and the magnitudes of the vectors in these three directions. For example, directions of vector A in 3D are AX, AY and AZ. Similarly, directions for B are given as BX, BY and BZ. To calculate the cross product, let us first check how these vectors will look like in 3D. where we have coordinates for A, vector A as 2, 3, 4, and for B it is 5, 6, 7. Now first check it out how it looks in this 3D setup. After that we will see how to solve this example. We have to identify the position of two given vectors in 3D space. 3D space in Cartesian coordinate system have three axes x, y and z. All of them begin with a single point called as origin. Now here we can see in given example the points for vector A bar are 2, 3, 4. That means coordinate of x are 2. We have to get x with two positions. After two positions on x, we have to move on y axis. Y coordinates are 3. After going to 3 positions on y axis, we have to get the height on z axis. Similarly, for vector B bar, the coordinates for x, y and z are 5, 6 and 7. That means on x axis we have to move 5 steps, then on y axis we have to move 6 steps. From there we have to go towards the positive z axis. That will be the given B bar. Now these two vectors situation in 3 dimension is clear in our mind. As given example is available, we have to imagine this setup in our minds so that we can understand the given physical appearance of these vectors in space. Okay, now let us solve this example. We have to put these values in the given formula. These are our routine 3 axes x, y and z. We have two vectors A bar and B bar. The angle between them theta. Just now we have seen where these A bar and B bar located in space. Now if we put these values in this formula where direction x, y, z, the magnitudes for A bar are 2, 3, 4 and for B bar it is 5, 6, 7. For solving this, first we will consider x axis. On its x axis, we have to take cross product of remaining two coordinate components. So say for x, we have to take cross product of y and z component as shown in figure. 3 into 7, it becomes 21. Similarly, we will subtract the components in another parallel cross product, which are 6 into 4. It gives 24. We have to subtract these values. In next step, we will consider values for y, but this should be subtracted from this x component values. So here we will subtract it. We will take y direction. For y, we have to take cross product of remaining two coordinate components as shown here. First, we will take product of 2 and 7, which is 14. Then we have to take product of 5 and 4, which is given by 20. We have to subtract them. At last, we have to add the z component as shown here. So plus z component. For z, we will take cross product from x and y columns. So it will come 2 into 6 as 12, 5 into 3, 15. So after solving this, we will get cross product of A and B. The values are minus 3x plus 6y minus 3z. So let us finally check where this cross product values looks in our 3D setup. Now we have solved this cross product of vector A bar and B bar. We have found out that cross product of A bar and B bar is located at minus 3, 6, minus 3. Let us first check it out the answer on a paper. On a paper, we can draw the vector A bar, B bar and their cross product. But we do not get much idea about how this cross product looks perpendicular to the vector A bar and B bar. We also lack the exact position of cross product due to 2D image. Let us enter into infinite 3D space and find out how exactly this cross product looks like. This is our coordinate system. We have already identified point B and point A. These points are representing the vector. So B bar and A bar are located in space as per the given instructions. Now we have to find out the position of A bar cross B bar. So its x coordinate is minus x. That means first our point should go on towards the minus x axis to 3 places. So this is our point on x axis, which is minus 3. After that, it should move on y axis, that is plus 6. So then this point should go towards positive 6 on y axis. So it will look like this. Then after that, it should go towards minus z axis to 3 places. Once again, let us check it. On minus x axis, it will go to 3 places, that is minus 3. Then it will go towards y axis to 6 places, and from there it will go towards minus z axis, and that will be the location where this A bar cross B bar is located. Now here we can see there are different angles to view this vector. So if we go closer and we find out the relation between these two, here we can see that these are perpendicular to each other. Any vector is making angle 90 degrees with their cross product. There we can see this is also making 90 degrees with another vector. But in two-dimensional, it is difficult to understand the exact position of these vectors. Our task is to imagine the setup in our mind while solving the examples. Now that's all for this session. We will leave you with few important vector identity at the ending of this session. Next session we will study few more new concepts in 3 dimensions. Till then, have a good time.